Hello y'all, we are Memphis Communiversity and we are doing another calculus done wrong lesson where we wrong calculus before calculus wrongs us. And today what we're going to be doing is we're going to be continuing our exploration of weird derivatives. In the last video, if you watched that, you know that we covered implicit differentiation where you take derivatives of equations without having to solve for y in terms of x. And we're going to be using that lesson for today's lesson, which is logarithmic differentiation. Keep in mind that logarithmic differentiation is a little bit weird. It's a lot less common than implicit differentiation. Implicit differentiation probably appears 2 to 3 to 4 times on each AP exam. I'm not even sure if logarithmic differentiation is even on the AP exam anymore, but it used to be certainly. And also, I've seen it on college calc exams the last time I took those for fun. So today we're still going to cover logarithmic differentiation. Also, it's not too bad. It's still taking derivatives. Derivatives is my favorite hobby in the world. It's so fun. So let's just get started. Let's talk about logarithmic differentiation. And you'll see that once we start listing out the steps and we apply the steps, it's not really anything new. So this is logarithmic differentiation. So logarithmic differentiation. Keep in mind that this is obviously a mouthful, so just like with implicit differentiation, I changed that to imp diff. We're going to call this log diff from now on. So let's do some log diff. So what is log diff used for? It's used for very specific functions. You don't want to use this process for every single function that you see. So let's talk about ones that you don't want to use it for as a counterexample. So if you know this function right here, x to the fourth, what's the derivative? Well, the derivative, of course, is you use the power rule, so you drop that power to the front like it's hot, then it's 4x, you subtract 1, of course. We've done this so many times. This derivative is 4x cubed. Let me write a y prime here. So that's that derivative. So another derivative that's pretty similar looking, but it's a completely different thing, is going to be y equals 4 to the x. What's this derivative? Well, this derivative is the ln a rule. It does come up quite a bit. Not as often as the power rule, of course, but it's something that's always good to know. So it's ln of a, which is ln of 4 in this case. Keep in mind, it's not ln x, ln 4. So this is, again, something to memorize. So if you look at this question, notice that x is in the base and a number is in the exponent. And then if you look at the next question, x becomes the exponent and you have a number as the base. So these are all old stuff. What do we use logarithmic differentiation for? Well, it's for functions that have x's in the base and the exponent. So that's going to be our strategy here. So let me just erase this real quick. You know the process, what we're going to do. We're going to do log diff today, so I'm going to erase this so we can have more space to write out steps. So all these questions, what they're going to look like is they're going to look like some function of x to some function of g. Meaning that both x's are in the base and the exponent as opposed to just one of them. If x is just in the base, then you're doing the power rule. If x is in the exponent, you're doing a to the x times ln a rule. This is for when there's x's in the base and the exponent, as we see. So for this one, I'm just going to list out the steps because they're easy to carry out. And then once I list out the steps, we're going to carry them out. So what's the first step? Why is this called logarithmic differentiation? It's because we take the natural log of both sides at the beginning of the question. We take the ln of both sides. So it's pretty aptly named. Logarithmic differentiation, how do you do it? You take the ln of both sides to start off with. So it's going to be ln y equals ln of this. And why do we do this? It's because of a log property from either pre-calculus or algebra 2. I don't know when you learn logs, but basically when you have a log of something, you're allowed to bring the exponent to the front. So this taking the ln changes this weird question where x is in the base, the exponent, to be a more regular question. So what we're going to do is we're just going to take it to the front. So this is the first step. Again, we take the ln of both sides. And why are we taking the ln of both sides? It's because we can take this guy and place it nice and gently right in the front. So that's what we're going to do here. And notice that when we have this function, it's going to be a regular function. So then the second step is going to be take the derivative. So derivative step. And I'm not taking the derivative of this thing, I'm taking the derivative of this guy and this guy because we dropped the power to the front. So the derivative of ln of y, as I said earlier, actually requires implicit differentiation. Remember that anytime you take the derivative of a y, when y is a function of x, you have to multiply by y prime because of the chain rule, because the n-side function is y. So what's the derivative of ln of y? It's going to be 1 over y, because it's ln, 1 over that thing, times y prime. And because you always have ln of y on the left side in these questions, you can always on this step, it's going to be y prime over y. Then you're going to take the derivative of this thing right here. Just keep in mind that when you take the derivative of this, first off, you're always going to have product rule, because you're going to be introducing a product in the first step. So the product will be the ln of the original base, so ln of f of x, times the old exponent that we brought down. So that's why it's always product rule. So I'm just going to write product rule. And keep in mind that this ln f of x, when you take that derivative, because the ln of an n-side function, you might be doing the chain rule. So we'll write product rule and maybe chain. This derivative should be a regular derivative. If logarithmic differentiation isn't on the AP exam, certainly derivatives of this type will be, as we'll see and once we do the examples. Sorry, I can't speak. Getting too excited. Because once you do these two steps, you actually did all the hard work. We're trying to isolate y prime. So what's the third step? You just bring the y over to the other side. So it's going to be y prime equals y, because we're just bringing the y over, cross multiplying it, and we're going to multiply it by the derivative of this function, which will be in step 2. So we're going to multiply by the derivative of this function, which we use the product rule for. And then we'll have y, and at the very end, what we're going to do is we're going to place the y with the original, and then actually our entire answer will be in terms of x, and it will just be a lovely day. So again, not a hard process. It's called log diff because you want to take ln's of both sides, ln of both sides. Why are we taking ln of both sides? So that we can drop the power to the front. Then when we take the derivative, it's always y prime over y, because that's the derivative of ln of y using impdiff from our previous video. And then this side will always be a product rule, potentially a chain rule as well if this function is a little bit more complicated. And then finally, we're going to bring the y over with a nice fell swoop, replace the y with the original, and you're good to go. So let's see how easy this is. Hopefully you've copied down these steps, but even if you didn't, we're going to be doing 4 to 5 questions or so hopefully those steps will be engraved. So I'm going to erase this right now. First log diff question, how exciting. If it's not on the AP exam, we're doing college level math, which is always fairly impressive. Let's get going. So my first question, let's keep it pretty simple for now. Let's just do x to the 3x. So this is my first function. First, let's note that we're doing logarithmic differentiation, and that's because we have x in the base and the exponent. Do not do the power rule, for example. Do not do the ln a to the x rule. This is logarithmic differentiation. So the first step is to take the ln of both sides. That's why it's called log diff. And why are we taking the ln of both sides? It's because we can take this 3x in our little hands here and just place it in the front. So that's going to be 3x ln x. That's good. So that's the algebra step. Now for the calculus step, what's the derivative of ln of y? Again, it's always going to be y prime over y, nothing too bad. And then just remember here that we have product rule. Don't get confused with this 3, just like normal, we have to have constants distributed to both sides of the product rule. So I'm going to underline this and this. So these might be my 2 parts of the product. So derivative of the first, that's just 3. Keep the same, ln x, plus derivative of 3. Just keep the same, sorry, 3x. And then derivative of ln of x, 1 over x. These can cancel if you want. I don't know how much your teacher likes to simplify. I don't really care about simplification, but these do, of course, cancel. So the next step is, or the final step actually, is to bring the y over and multiply it by this thing. 3 ln x plus 3, because the x is canceled. And then we're going to bring the y over, so I'm just going to multiply this by y. But remember that y is originally x to the 3x, so I'm going to replace with that, and then I'm going to be done. Notice how easy this process is. Not too crazy, not too crazy, not too crazy. Don't know what I'm saying anymore, but I do know how to do this. And you will know how to do this because it's not too bad. Again, ln both sides, bring the exponent to the front, y prime over y on the y side, product rule on the x side, bring the y over, replace the y with the original. So let's see what you got here. I'm going to erase this and do another question. Let's erase this, erase this, erase, 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 erase. So let's do another question. Let's do y is equal to sine of x to the x squared. So again, we do have log diff on our hands here because we have something in the base with x's and something in the exponent with x's. So what we're going to do is we're going to take the ln of both sides. Right here, if you will have your paper here, you can probably write ln's here, but whatever. And we're doing this not because of this guy, but we can bring this guy to the front. So this is going to be x squared ln sine x. So now for the fun, now for calculus, always on the ln y side, when you take the derivative, it's going to be y prime over y, because the derivative is 1 over y times y prime, because it's implicit. Then we have a little product rule situation going on, but we can handle it. The derivative of x squared, of course, is 2x. We're going to keep ln sine x the same. Then we are going to keep x squared the same. And now we are going to multiply by the derivative of ln sine x. Keep in mind that we did introduce ln throughout this process, and that's why we're going to have to be doing chain rule, because sine x is within ln x. So what's the derivative here? It's going to be 1 over sine x, 1 over whatever is in the ln. But because of the chain rule, we do need to multiply by the derivative of the inside function. What's the derivative of the inside function? Well, that's just going to be cosine x. So I'm going to change the numerator here to be cosine x. So that's the calculus step. Again, the most important thing by far, and a little nice review of derivatives, is this guy right here. So let's finish the question. The easiest step, just take this y, bring it nicely to the other side. So we're going to rewrite this in parentheses, 2x ln sine x plus x squared. If you were feeling a little bit bold, you might realize that cosine x over sine x is cotangent x, so we might as well change it to that so we don't have fractions. And then finally, we're bringing the y over, but what is y in the very beginning? I can write a y for you. What some of my students do is they'll just take the y, they'll write a y and immediately erase it. Some of them are a little bit less lazy, so they'll rewrite this. But again, just replace the y with the original. So I'm going to erase this. I'll be lazy. We'll erase it to the original, and this is the derivative. Again, not too bad of a process. Take the ln of both sides. Drop the thing to the front. Derivative y prime over y on one side, product rule on the other. Bring the y over, substitute in y. So let's try to do a harder variation of this. So we have this. Let's just see what we got. Maybe a few more questions here and there. Let's do y is equal to, let's do ln x to the secant of 3x. So part of the reason why I do this lesson is just to cover derivatives, because derivatives is the most important skill in Calculus 1, in the first half of calculus, so this is a good way to review chain rule and product rule and things like that. But let's take this derivative. So first thing again is to take the ln of both sides. So we're doing ln of this crazy thing. Keep in mind that we have ln of ln here, but it's not going to be too crazy. We're going to take this secant 3x, bring it to the front. That's why we are doing this process in the beginning. Ln x. And then let's start taking derivatives now because we brought it to the front. Ln y's derivative has been the same for the entire video. It'll be the same for all eternity, I guess. Ln of y is y prime over y. And then you don't have to look at this middle step because that's the bad step. That's when you have x to the base of the exponent. We brought it down, so let's take the derivative of this product rule. It might be a little bit tricky, but I believe in us. So what's the derivative of secant 3x? Remember that the derivative of secant x is secant x tan x, and you put 3x in both slots. So it's going to be secant x 3x tan 3x. And then, of course, we need the chain rule. What's the derivative of 3x? It's times 3. Because that's the original inside function. Looks like I'm running out of space here. I might panic. We'll see what happens. Keep the same for the rest of this half of the product rule. So this is the first half of the product rule. Derivative, so this entire thing was a derivative of the underlying thing. We kept the same with the double underlying thing. Then we're going to write plus Do the second half of the product rule. Keep this guy the same, secant 3x. And then what's the derivative of ln of ln? Well, it's going to be 1 over the thing in the ln. That's 1 over ln of x. And then we do need to multiply by the derivative of the inside function. Chain rule is so important. That's going to be 1 over x. That's the hard step. Just remember the final last step, it's the easiest step. Take this y, let's be as lazy as possible. So instead of writing y prime times 1 over y, what we're going to do is we're just going to multiply by y so we don't have to rewrite it. So we're going to multiply this by y. But then remember that you can sub in y for this thing, so we can erase this. And instead of y, we can write this. ln x secant 3x. Ran out of room there, but hopefully you see the process. Nothing crazy. This is the same method every single time, just harder and harder derivatives, but there's no hard derivatives actually once you get used to derivatives. So this process isn't too bad. So let me erase this one right here, let you practice a little bit, and then let's come back. So let's do this guy right here. Let's just practice one more time. Let's take the derivative of, let's do tan to the negative 1 x to the 7 to the x. Let's do 7 to the x squared. So we have this function to this function. So it's going to be kind of complicated. Let's change the question a little bit to add a little bit of chain rule, because I love chain rule. Let's change it to x cubed. So we're going to do this question, still using log diff because x is in the base of the exponent. Why don't you pause your video, try to practice this one. I'm going to be right here. I'm not going to leave, I promise. And just try this for 3, 2, 1. Let's just see what you got. So we're doing log diff, taking the ln of both sides. So we're going to get ln of this thing right here. Let me rewrite it better. X cubed, 7x squared. What a crazy derivative, but I believe in us. We can do it, team. We can do it. So why are we taking the ln of both sides? Because we can drop this weird exponent to the front. So it's going to be 7x squared ln of 10 to the negative 1 of x cubed. I don't know why I wrote another cubed. You can't see what I'm doing right now, but I'm just doing bad things. So hopefully I can cover that up before you see. But notice all we did was drop the 7x squared. So now it's time for the product rule. So y prime over y on this side. And then start taking the derivative. Let's keep this one the same. And then we'll take the derivative of this guy right here. So it's going to be 7x squared, keeping this the same. Then it's ln, so ln is 1 over that thing. 1 over 10 to the negative 1 of x cubed. Then this is a little double chain rule just to add to the fun. What's the derivative of inverse tan? Remember that's 1 over 1 plus x squared. So in this case, it's going to be 1 over 1 plus x cubed squared. Keep in mind that by exponent rules, this is x to the 6th and not x to the 5th because you multiply the exponents. And then we do need to finish the chain rule. Remember that there's still an inside function, so we need to multiply that by 3x squared. The derivative of x to the cube because we did the power rule. That's the first half of the product rule. Let's do the second half. So this is 7 to the x squared. So it's going to be 7 to the x squared times ln 7, because this is the a to the x rule, a to the x times ln a. Then we still have an inside function, so we're going to multiply that by 2x. And then finally, we're going to keep it the same. So it's going to be ln of 10 negative 1 x cubed. And then finally, as you can notice, I've run out of board space, so I can't rewrite this. Hopefully you can tell that this is 2 lines. I forgot my plus. But this is the product rule. Do I have too many parentheses? Whatever. And then, so this is the first half of the product rule, second half of the product rule, and then finally we're going to bring over that y. So bringing over this y, and then we'll write y, but then we're just going to put this. Let's see if I can fit it in here. 7x squared, very, very sloppy. towards the conclusion of this question, but hopefully you can still see that the process is the same. Basically, the only difficulty from this question could just be how hard a derivative is. So that's that. Those are some hard questions. Those are some easy questions. They're the same level of difficulty in my opinion. So just keep in mind though that I'm sure that you love this process. I'm sure everybody loves the logarithmic differentiation. It's our favorite thing in the world, I know, but just stay calm. Don't do this for every single exponent you see. Remember, we're only doing this when we have x in the base and x in the exponent. So, just for kicks and giggles, if that's a phrase, I don't know. If you have something like this, remember that this, because pi is not an x, this derivative would just be the power rule, our old friend. So it just wouldn't make sense to do all this hard process when you can just go straight to the derivative, dropping the power down, subtracting 1 of course. Same thing for this. If you have, I don't know, 4 to the sine squared x, this is not logarithmic differentiation. This is just regular derivatives. I'll take this derivative real quick because it's a nice derivative. I rewrite it like this so I can employ the power rule easier. And this is the a to the x rule, a to the x times ln a. So y prime is equal to 4 times this thing times ln 4, because that's the rule, a to the x times ln a. Then we multiply by the derivative, the exponent, which is the inside function. But then we have to multiply by the derivative of the insidus function, the inside of the inside, which is going to be cosine x. So let me erase this. Ln of 4 times 2 times sine x times cosine x. But the point of this little thing is that while we do have logarithmic differentiation sort of in our tool belt now, we don't want to use it too often. We only want to use it when it applies, and that's when x's are on the base and the exponent. Last thing, let's see if you understand this. I'm going to have a little brain teaser, always nice to tease the brain. We're going to have one function that I saw on a math test once before, and I thought it was pretty nice. Let's do the last question of y equals x to the x to the x. So not just base and exponent, but base and exponent and exponent. So I'm just going to do this one real quick. It is logarithmic differentiation because you have so many x's. So it's going to be ln of y equals ln of this fun thing. And the reason we're doing this is to bring down the exponent. So let's bring down the x to the x. Then we're going to take this derivative. Always the derivative on the ln of y side is y prime over y. Then I have product rule here, so keep the same. And then derivative, so keep the same times the derivative, 1 over x. Then it's going to be kind of weird because you have to take the derivative and keep the same. But unfortunately, x to the x requires its own logarithmic differentiation because it's x to the x, but it's the simplest version. So let's just do it on the top here and show that it's not very difficult. Let's not use y because y is right here. Let's use z instead. So z is equal to x to the x. Again, I'm doing this because I need to take the derivative of x to the x for this half of the product rule. So we're going to take the ln of both sides. We're going to drop this x to the front. This is usually the first example in calculus textbooks of logarithmic differentiation. What's the derivative of ln of z? Just like the derivative of ln of y is y prime over y. This is going to be z prime over z. And then we're going to do product rule here, but this one's a lot simpler. Derivative of x is 1 times ln x plus keep the same derivative, so it's going to be x times 1 over x. I'm running out of room here, as you can tell. Let me erase this little line, make it a little bit neater. So this cancels out, so notice this side is just ln of x plus 1. And then we're going to bring the z over. But what was z? Z in the very beginning was this thing that we're trying to take the derivative of. How crazy. So it's going to be x to the x. So this is the derivative of x to the x. So to finish this question, what we need to do is we need to take this guy, put it right here. So let's move this over. So we're doing the second half of the product rule. What's the derivative of this? Well, we just found it. It's kind of complicated, but we were able to find it in the end. And then finally, keep the same. So we're just going to write ln of x again.
This is getting very, very sloppy, just like the previous example. What are you going to do? Finally, let's end this question. Let's end this monstrosity. Bring the y over. The y was originally x to the x to the x. So it's x to the x to the x times all of this. You can simplify a little bit. For example, this becomes x to the x minus 1. Again, because of exponent rules, you subtract. And then over here, we have x to the x, ln of x plus 1 times ln of x. And I think we are good to go. So this last question wasn't too important, but hopefully you can see that you can make these questions a little bit trickier by adding more exponents, but it's still the same process. Not the most important question of not the most important lesson, but hopefully you got something out of this. If anything, after you learn the logarithmic process, which is take the ln of both sides, drop the power to the front, y prime over y equals product rule, maybe chain rule, and then bring the y over sub, that process that we talked about for like the past 25 minutes or so. Once you've gotten down that process, hopefully you will be able to apply it whenever you need to, which is in the x in the base and the exponent. And also this process, doing these practice questions, will help you review derivatives, which is always pretty nice, of course. Again, just like normal, we have a Girls Teach Calculus video in the description below, so go check that out if you want to practice more of these logarithmic differentiation questions. Until then, thanks again for watching, and I hope to see you next time. Thanks again.